Hello class, today I want to show you a little bit about expressions and encourage you to use this option for getting some data. It will be easier because maybe I haven't give you that much tools how to extract the data. Usually we go through like a plot, manually extract some data, or we can extract profiles, but expressions also can help us a lot. For this simulation, because it's just showcase, I draw this larger box, which is going to be our air domain, and small block, this cube inside that, is going to be our cube inside this air domain. It is going to be the simulation, something like a flow inside internal or channel. So if I remove my block, you're going to see we have that sharing contact between the air and block. So everything is good, no problem. Let me show you a few details what I've done, so it will be useful later. Okay, let's go back to our mesh. Let me show you the namings we have so we can have a better understanding of the geometry. Okay, I named this side as an inlet, the other side outlet. These three and lower part is going to be our walls, the side walls, so nothing important is going to happen there. And I named the block there, air there, and the bottom surface of the block as block B to assign some temperature if I want later, and the contact between block and air, I put the name. One of them from the air side, I made it block side 2. From block side, it's block sides. Let me, for example, hide block so you can see what I mean. This is the surface I selected because it is going to be the surface of the block inside that air. So later, if I need any information about that, I already named it. Okay, so I put just general mesh. As you can see here, I have some inflation around the block because we usually close to the wall. We need more information. This is a rough mesh. I didn't go for high quality mesh. Just this is the showcase, but I wanted to show you whenever there is a wall and it is important for me, I need to have inflation. Okay, good. Now let's go and I assigned, okay, let me open this. I assigned air for the fluid and aluminum for the block. So very simple materials. Basically, those are the default materials for ANSYS Fluent. Okay, almost there. So you can see it's a pressure-based, transient. I included gravity, but of course gravity is not that much important. Models I consider to be SST K omega because velocity I decided to go with, I don't know, 10 or 15 meter per second. So probably it would be turbulent flow inside this channel. Energy on because I want to have temperature effect. Fluids is air and solids is going to be aluminum. Cell condition for the air part is fluid and it's air. For the block part it's solid and it is aluminum. Boundary conditions, you can see inlet is inlet, so I already named them, so it is easy to check. So it is 10 meter per second for the inlet and the temperature is 25. And outlet is pressure outlet. As you know, the pressure outlet is the easiest boundary layer. Basically you make pressure outside 0, gauge pressure would be 0, and again the temperature is going to be 25. So many students usually forget about this, and then you can see in their simulation they have a hot fluid coming from outside, which is because they haven't assigned the initial or room temperature when they are assigning their boundary conditions. Anyway, and for the side walls it's wall. Then you need to make sure your interface is okay. You go to the contact region, edit, and when you select this, you should couple the walls, the contact between the block inside and air around it. We must have thermally coupled to be able to have heat transfer from the block to the air and having that cooling effect happening there. And nothing else. I kept everything as a default. The method is this, nothing changed here. And I saved some data, as you can see here. Let me show you from the top: pressure, velocity, XYZ, and temperature, wall temperature, Y plus, and kinetic energy, density, dissipation, turbulent density, wall Y plus in case I need, wall shear stress, and surface heat transfer coefficient. If I want to calculate Nusselt number, I need to know what is H at the surface. So this is good, handy. You can have total surface heat flux, skin friction in case you need to other type of calculation, and you can have heat transfer coefficient with different formulas in terms of if you are using wall function, you can have wall function heat transfer coefficient. You can have surface Nusselt number 2. So I included a few data, and for every 2 time step, they're going to be saved in my desktop. Okay, then I initialized Let me check. Initialized and patched it, and I put high temperature as the initial temperature for the block, gradually to cool it down. It was like a 250 degrees, something like that. And then I decided to go with this time step. Usually you need to check your CFL number to make sure this time step in relation to your mesh size, it's a proper number, and for a few time steps to get a few seconds of data. So after finishing the simulation, I got this results. Let me go back to the counter. Let's show you plan 1 velocity, for example. I can close. So this is my air domain. As you can see, it's the air domain, and block is here. We have inlet from the left and outlet here, and we have nice flow around the block. As you can see, it's to the left, to the right. It's going to kind of flap a little bit at this Reynolds number, whatever the Reynolds number is. So, and interestingly, close to the sidewalls, because we have no slip condition, you can see the velocity is blue, shows the zero velocity. So it is working close to the block. Also, we have lower velocities, but of course, because of the high velocity, the boundary layer is smaller, and you can see the wakes behind and circulating or turbulence behind the this block, which shows the type of flow we have. Okay, so this is the velocity. You can, I draw this plane number 1. You can draw any other plane or line anywhere you want to get information about that. But these are qualitative data. You may need quantitative data. Let me show you, for example, plan 2. If I use this, show plan 2, you're going to have velocity over the plan 2, which is vertical. I wanted to see what is going to happen at this perspective, and you can see this is the okay, I should have selected the other way. Anyway, this is our block, and low velocity around it, and gradual velocity increases and then decreases. Okay, so the main purpose of this video is not about the simulation. You're familiar with this type of simulation, very easy for you. Let's go to expressions here. Let me increase the size. So we have variables and expressions, which they are very useful. I defined a few expressions already here to show you how it works, but of course I'm going to show you the details how we can define expression. For example, the first one I wanted to know is Reynolds number. So let's double click the Reynolds number. So here it says 1.225 kilogram per meter cube. So it's a density. I manually type this with the unit times 0.045461 meter, which is our characteristic length. How I did this, found this for this channel. Basically, I found hydraulic diameter and selected that hydraulic diameter as my characteristic length. So it is 30 by 100. So 4 times cross-sectional area divided by parameter is going to be hydraulic diameter. So it is going to be 4 times 3 times 100 divided by 130 times 2. That's it. It's going to be 0.0461 times velocity. But I have maybe different velocities at the here, but the best choice would be the average velocity. So I said area average for velocity. Which side? I just want x velocity because I already defined only x velocity here as an inlet. Where at sign inlet. Inlet is the name I already defined in my simulation when I was defining my mesh, divided by viscosity. So I am using the air viscosity from the material properties of the ANSYS. So I copy it and paste it here. So if I click this, you're going to see it says my Reynolds number at inlet is 31,566.5. And because I included all the units, it's dimensionless, so it is correct. I can do for skin friction, wall friction, for example, CF. I don't know what you call for your fluid mechanics subject, but again, I wanted to have area averaged skin friction at this place. This place, if you remember from the mesh part, when I was naming, I named block side 2, which is the contact between the block and air. So basically, this formula or expression gives me skin friction average, area average skin friction of the block. So if you want to do any calculation and you need skin friction to calculate, for example, shear stress, you can use this average skin friction as for the whole, which is 0.012, and do your calculation. Let me show you another one, which is I define Nusselt number. Okay, for Nusselt number, it was much easier because I asked ANSYS to give me the area average of the data I already selected to extract for me, which is surface heat transfer coefficient. Where, again, at the surface of the block, because I want to have overall average Nusselt number for the whole surface. And so H times the characteristic length, which is again, it can be any size for the you prefer, but of course you need to just report, for example, this can be the length of this block, any length you want, and divided by thermal conductivity of the fluid, which is air. So I divided by thermal conductivity. If you apply, it's going to be 216. And don't pay attention for this negative. It depends on the which contact surface I select. It can be positive or negative. If this is from the block side, it's going to be negative. If it's from air side, it's going to be positive. So no big deal there. Okay, for this plan, which we called it plan 2 here. So this plan. Let me turn it up. So this plan, I want to see what is the maximum velocity over this plan. What is the maximum velocity? So I go to expression, and I define another expression which says maximum maximum value of velocity, one of the data I extracted already at plan 2. So the system or the ANSYS is going to check all the velocities here, and it's going to give me the maximum velocity of 12.6. From here you can see it should be 12 point something. So it's fine. So let me go back and make this. Okay, let me draw another plane. This time, plane number 3. Let's turn off this, and it is going to be at similar to plane number 2, but at the end of the other end of the block. So it is going to be at ZY. Let's see, what is it? So let's make it a bit closer to the block. Yeah. So now I have another plane, the other side, and I want to get the average velocity at this part. The plane name was plane number 3. So I'm going to define an expression, right click over expression, new. Let's call it velocity average 2, because I already had one. So what I'm going to do is I want to find a value. It can be maximum, it can be minimum. Minimum, it's always 0. So for velocity, so I don't care that much about minimum. It can be an average velocity if you have some application, or maximum. So I'm going to select functions from CFD post, and I have so many functions available. I can find the area average, integrate over area, count something, normal force, as you can see, length average, everything. So I can select minimum value, maximum value, sum of some stuff. So if you have, for example, I don't know, some type of variable which you want to add all the, for example, I don't know what variable would be useful to sum them. Anyway, it would be, you can use those stuff. So let's go for maximum value of what? Maximum value of one of the variable I already asked. That is why when you doing simulation, try to include as many as variables as possible, because later say, oh, I needed this, I needed that, so it would be difficult. So this time I can select it, shear stress, turbulence. Let's go with x direction velocity, so velocity u this time, where I want to be at this surface. So it's going to be location plane 3, but you can select all of these locations, some of them coming from the naming you had when you defining your mesh. So let's go with plane 3, and that's it. If you want to multiply it with some number, make it dimensionless, you can divide it with any number, you can do it here, but for now it's okay. Apply, and you can see, okay, the maximum velocity, x velocity, is 11.34 meter per second at plane 3.